Hey guys, welcome back. We're moving on to our next unit, which is inference for proportions. So this is a pretty interesting unit, and it transitions really well from the binomial model that we did before. So let's look at sampling distribution models, and we're going to answer the question, what is the proportion of green M&Ms? So there's obviously, looks like there's quite a bit here, and it looks really good, but how many M&Ms, what proportion, or in other words, what percent of all M&Ms are green? Now there is a true proportion out there that exists, right? Of all the M&Ms that have ever been made, there's a certain percent of them that are green. And then we can actually select samples of M&Ms to try to get a better understanding and draw some sort of inference about the true proportion of M&Ms, and we'll be able to create confidence intervals and do hypothesis testing and stuff like that. In fact, we'll even do this in class, of course, when we're back in class, and I'll give you guys little bags of M&Ms, and from those M&Ms we'll be able to determine and make some inferences and draw some conclusions based on our samples. And to be honest, this is really the crux of all of statistics, is based on inferences based on samples. So welcome to probably the most important unit of all of statistics. So here we have sampling distributions of sample proportions. So let's say that we have, out of 10 M&Ms, let's say that the true proportion is 16%. So the true proportion of all M&Ms that are green are 16%, which is kind of sad because green is my favorite color, and it's one of the rarest ones. I think brown is the rarest, but anyway, so out of 10, if we're expecting 16% of them to be green, then the expected value would be 1.6. So on average, we'd expect 1.6 out of every sample of 10 we'd have 1.6 green ones. And that's a binomial. With small samples like that, because we're not expecting 10 successes, we're only 1.6, clearly it's going to be skewed to the left. So this is not, it's going to get cut off by the hard left bound of 0, right? So our distribution will be skewed to the left. But as we increase our sample size to a sample size of 50 M&Ms, for instance, maybe the amount that are in a small bag of M&Ms, now if we multiply N times P, 16% of 50 is 8. So now we're expecting 8 successes, which is almost large enough for us to be able to use a normal model, right? So not surprisingly, it's no longer skewed. It's not going to be cut off by the left bound of 0 anymore. In fact, this one would actually be okay for us to use it, but it doesn't satisfy our success failure condition. So we will still use a binomial for this one. Now, the proportion that we would expect is 16% of these. And the difference is we're dealing with, out of a certain number, how many expected successes, which is the binomial. But then we're going to convert this to proportions, which is going to be a percentage. So one thing you notice is that as we increase our sample size, any distribution, the mean of any distribution, becomes more nearly normal, or even the proportions will become more nearly normal as the sample size grows. So even though it started out skewed to the right, as we increase the sample size, the central limit theorem guarantees that we'll become more nearly normal. Now, the central limit theorem is actually also known as another name as the fundamental theorem of statistics. And when we get to sampling means, where we can have distributions that are not based on the binomial, but rather can be based on anything like multimodal, unimodal, or heavily skewed distributions, the fact that our sampling distributions is always going to be normal regardless of the shape of the distribution of the population is absolutely fascinating. So the central limit theorem is kind of like a light version that we're talking about right now, but it will become really, 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 really cool when we revisit it in the next unit. So anyway, moving on from that, it is the central idea of all of statistics, by the way. All right, so then what would the spread be? So if we were expecting 16 successes, we found the spread before as N times P times Q, and we take the square root of that. Well, if we put that in the calculator, we'll get 3.67. Now, the difference is whenever we're talking about proportions, it's a percentage. So out of 100, what percent is 16? Well, we need to change these values now by dividing them all by N, which is dividing it by 100. So 16 is going to be 0.16% or 16%. Okay, and the same thing, you just notice the decimals move twice because we're dividing everything by 100, and that's how we get it from how many successes we're expecting to the percentage. So our standard deviation is also going to be divided by the n to get it into percentage. So basically we're just scaling by 1/100th. So whenever we put that in the calculator, there's two things we can actually do when we're simplifying this formula. Instead of dividing by n, we could actually divide by the square root of n squared, because the square root and the n squared will undo each other. They're inverse operations, at least for exponents. And so now that both of these are under the square root, we can put them under the same square root because they're to the same power. We kind of factor out that square root. So under one big radical, that we can also reduce because we have an n on the top and two n's on the bottom, we would have the square root of p times q divided by n. And this will be our formula for standard deviation. For the binomial, it was square root of n times p times q. For proportions, it's going to be p times q divided by n, and then we take the square root of all that. So when we do that, essentially we get just this scaled down. It should look familiar, but it's just scaled down with the decimal moved over twice. So 1, 2. So what was happening here? Well, we went from the binomial, which is all the parts in red, which we're very familiar with, to dividing everything by n, including our standard deviation, which moved the decimal over twice because n was 100. I picked an easy number on this one. And now we're dealing with proportions. So what's happening is we're scaling. So if you remember, like the dice, we have outcomes of 1 through 6. We could double the dice. So whatever you roll, let's assume you rolled a pair of them. So now it could be 2, 4, 6, 8, 10, or 12. And notice our spread is doubled as well. But another way of scaling is actually by dividing. And so if we divide everything by n to get to the percentage, what's going to happen to our standard deviation? Well, our mean is going to be divided by n, and our standard deviation would also be divided by n as well. So if we divided everything by 6, then the expected value would be divided by 6, the standard deviation would be divided by 6, and the variance would be, it's going to be basically divided by 6 squared, in other words. So the, whatever our scale factor was squared in this case. All right, so measuring the spread for the standard deviation, and for proportions, like we said here, same thing with scaling. All we're doing is dividing by n, which in this case, instead of expecting 16, we divided by 100, which gave us 0.16. And for the standard deviation, also gets divided by 100. So instead of 3.67, it's going to be 0.0366, which actually repeats, but you get the idea. All right, so now we need to go back to one of our topics from Unit 3, which is gathering data. So we have a population and the sample. So a population is going to be like the set of all, so it's like the set of all M&Ms in this case, or like our big soup. And we want to draw conclusions based on samples about the soup. So we want to know, is the soup that we're making, is it salty enough? Is it too thin? Is it too thick? Do we need to add more water to it? Are the peas done? Whatever we might want to know. These are going to be sample statistics. So the true value of the amount of salt that's in here is the population parameter. And whatever we get from our sample is called a sample statistic. So whatever questions we're asking, in this course, we'll be mainly asking about proportions, which are percentages, and means. So like what's the average height or the average waist size for American males, or whatever we're interested in, or percentages, like how many M&Ms, what percent of M&Ms are green in the whole proportion and the whole population. All right, we draw samples to make conclusions about the population itself. The samples, in this case for proportions, are going to be p hats. The hats tells us that it came from the sample. The true proportion would just be a p in this case. All right, so the population is the entire group of individuals being examined. What we're examining is being called the population parameter, so we're trying to make inferences about. The sample is a group of individuals selected to represent the population. We're hoping it's representative of all the stuff about it being independent and randomized to make sure we do avoid bias. That's all still at play. The summaries of the data we collect from the samples called the sample statistics. For instance, in this case, they'll be proportions. So what percent of M&Ms that we collected were green? So in our example, the true proportion exists. That's going to be the actual amount of all the M&Ms out there, what percent of them are green. So this is going to be a whole, all the possible M&Ms out there. It's kind of fun. Then we have something called a sampling frame. The sampling frame is going to be what we are drawing from. So we want to try to match our sampling frame with the population as best we can. So for instance, if we have a list of all registered voters and we're drawing from that list, that would be our sampling frame. And hopefully all the people who are voting are all registered voters, etc., etc. So in this case, that would be a bunch of little fun-sized bags of M&Ms that I bought from the store. That would be my sampling frame. Now I'm hoping my sampling frame is representative of the actual population, but again, it's kind of like its own little mini sample. So you do the best to match those up as best you can. And then we draw from that bowl of little M&Ms, and then I give you an M&M, and then we basically draw those out. So we pull out one of the bags of the M&Ms, and then we sort it out and we analyze it, and we look for a proportion. So let's say out of 50 M&Ms, we found 12 of them that were green. So 12 out of 50 would give us a sample proportion, notice it has a hat over it, of 24%. Now the true proportion, they say, from M&M, Mars and Mars, they say that it's actually 16%, but our sample suggests that it's 24%. So of course we're not going to expect every single bag of M&Ms to have exactly 16% of the 50, which is roughly 8, I believe. So we're not going to expect all of them to have exactly 8 green M&Ms. Of course, there's going to be variation from sample to sample, and it's actually the measure of the variation that allows us to draw conclusions to decide when it's an unusual enough sample for us to be able to call BS on the original population. And that's also why we have margin of error whenever we're drawing conclusions from a sample, because of sampling variation. Just because our sample said that there were 24 in the bag of 50 M&Ms does not mean that there's exactly 24. We believe exactly 24% of all M&Ms are green. We're going to have some sort of margin of error there. So we'll say plus or minus 10%. And if we did plus or minus 10%, that would be anywhere from 14% all the way up to 34%, which actually would successfully capture the true population proportion. All right, so I'm going to stop rambling, but this is like a really good slide, and that was a really good explanation, so you're welcome. All right, sampling distribution models for a sampling proportion. All right, so from that we can build a sampling distribution model. So if we took a whole bunch of samples, so every single one of those bags that we bought, and we analyzed the proportion for each one of them, and we started stacking them together. So one of them we put together was 24%. Then we get another one which is going to be 20%, another one which is 11%, another one which is 5%. And we put them all together. Eventually it's going to build and form a bell curve, which is from the central limit theorem. So cool. And that is called the sampling distribution model. So the sampling distribution model is a distribution of all possible samples. And it's a model, it's like a normal model. It's pretty cool. So we abbreviate that SDM, sampling distribution model, for the true proportion of 16%. It would, on average, all of our proportions would be 16%, if that's the true proportion. And then the 50 is going to tell us the sample size. The larger our sample size, the less variation in the samples. We're going to be able to make more conclusive results with less variation, a smaller margin of error and stuff like that. So our sampling distribution model has two parameters. It has the true proportion, whatever that value is, and then the second part is going to be the size of the sample. Okay, so I think that's pretty much it. If assumptions of independence and random sampling are met, and we expect at least 10 successes and failures, then the sampling distribution of a proportion is modeled by a normal model with a mean equal to the true proportion value p, and the standard deviation equal to this part right here. So p times q divided by n, take the square root of that. So the reason it has to be randomly selected is that if we don't randomization, it helps us avoid bias. So it also helps us to guarantee that there wasn't any bias in our sampling methods that might make the sample not representative. So it's not over or underrepresenting any part of the population. The 10% condition has to do with independence. So if we're not drawing an independent sample and they're actually more likely to be related to each other, for instance, if M&Ms that came from a certain factory are going to have a higher proportion than if we all got them from the same factory, then of course all of our samples will be drawn towards the higher proportion or whatever. So it's important it's independent as well. Success, failure, of course that makes sure that it's normally distributed and not too close to either 0 or a hard left bound of 0 or a hard right bound of n. So we need to make sure we have at least 10 successes and 10 failures to guarantee 3 standard deviations unobstructed by our hard bounds. So those are our 3 conditions for us to do sampling distribution models. Hopefully all that makes sense. So independence, we can have that from a coin or from dice because they're always independent. They reset. Coins don't know what they flipped before. Dice reset every time too. If we're dealing with cards, we have to make sure that we shuffle them, riffle shuffle 7 times in between each draw. Otherwise, there's going to be a residual of the pattern from whatever you did before. You'll notice that especially if you play Go Fish and you have them all paired up. Then if you only shuffle it once or twice, you're going to have a lot of pairs that are still stuck together. It's kind of cool. But anytime we're sampling without replacement, it's not actually going to be independent, because if we draw an ace, or if we draw two aces, we know the probability that another ace is out there is actually only 2 out of however many cards are left. So drawing an ace is going to change the probability of drawing another ace. So we override the fact that we know it's not independent with the 10% condition. So our assumption of independence is no longer, it's out the door, but we can override that with the 10% condition as long as we're sampling less than 10% of the entire population. So in a deck of cards, that's 52 cards, so 10% of 52 would be 5.2. So essentially, as long as we're sampling less than 5 cards at a time, we're okay. We can override it. The probabilities we know are not independent. They're going to change, but they're going to change so the change is going to be so small that it won't throw off our overall results. Success failure condition, make sure that it's going to be nearly normal, meaning that it's not going to be cut off. We have enough successes so that it's not cut off. It will eventually, as we increase our sample size, everything turns into a bell curve. So cool. Central limit, most important thing, central limit theorem. Okay, but it will be cut off by a hard left bounds if we don't have at least 10 successes and 10 failures. So showing that here, like I showed before, there's the math. You can go back and look at it if you want to. But if we have less than 10 successes that we're expecting, let me lock that in place, then all this stuff that went to the left of 0 is going to get piled up right here at 0. Okay, and if we don't expect at least 10 failures, then all this stuff that would be over on the right side of n is all going to get piled up here, and then the distribution is skewed to the right or skewed to the left depending on what you're looking at. So we need to have at least, the mean is expecting at least 10 successes and at least 10 failures on both sides, depending on which one is the closest to 1. Alright, so what would be considered unusual? So in our sampling distribution model, anything that is more than 2 standard deviations away from the mean, or has a z-score higher, or with the magnitude more than 2, whether positive or negative, would be considered an unusual proportion. So if in our little fun-sized bag of M&Ms we had 26.4 or more percent that were green, that would be a really unusual bag. If we had less than 5.6% that were green, multiply that by 50 and you figure out the exact count, in case that's what you're interested in, then we would consider that an unusual as well. So our expected value is going to be n times p from the binomial divided by n, which just is back to p, which is 16%. That's where it's centered. And then for the standard deviation, it's p times q divided by n. In this case, our p and q is going to be 16% and 84% divided by 100 for our sample size, which will give us 5.2%. All right. Now, the sampling distribution model, if we write SDM, stands for sampling distribution model, with parameters of the proportion of 16%, true proportion, and the sample size of 50. I guess we were doing 100. I don't remember. I think this is actually 50. Yeah, I need to change that. It should actually say 50. And you'll notice because our standard deviation is higher than it was before when we did 100 for a moment there. All right, then we can also say that this is a normal model centered at 16% with a standard deviation of 0.052. So notice one of them is showing us a sample size and the other one showing the standard deviation, depending if you're parameterizing as a normal model or if you're using as a sampling distribution model, but they're really one and the same. Just depends on the context. All right, so let's go ahead and start the assignment. So 18 minutes. We are starting a new unit, so that's not too bad. There's always a lot of new material for me to cover when we have new units, so I think that went pretty smooth. I'll try to, of course, make the lesson tomorrow shorter. Number 12, M&Ms. The candy company claims that 16% of milk chocolate M&Ms that are produced are green. Suppose that the candies are thoroughly mixed and packaged into small bags containing about 50 M&Ms. A class of elementary school students learning about percentage opens several bags, counts the various colors of candies, and calculates a proportion that are green. If we plot a histogram showing the proportions of the green candies in the various bags, what shape would we expect it to have? Well, as we found, because of the central limit theorem, regardless of what the true population of the shape of the population, our sampling distribution model will always become nearly normal as long as we have a large enough sample. So we would actually expect it to turn into a normal model. So it would be the binomial. In this case, where we're expecting 50, and then 0.16 is going to be our true proportion. So that's the value for p. All right, so we would expect to be unimodal and symmetric. Can a histogram be approximated by a normal model? So we always start out with a binomial, and then if we have at least 10 successes and 10 failures, we can apply a normal model to it. Unfortunately, 16% of 50 is going to be 8. We're only expecting 8 successes, that's the mean, which is not more than 10 or equal to 10, so we can't use a normal model because it wasn't quite big enough. We're not expecting enough successes in order for us to guarantee, by the worst case scenario, that we would have at least 3 standard deviations unobstructed by 0 or by n. So where should the center of the histogram be for our binomial? Well, n times p we said was 8, right? So it'd be centered at 8. With a standard deviation of n times p times q. So we're not doing this as proportions. This is actually still sticking with the binomial for a moment here. So that would be a standard deviation of 2.6 essentially. So if you wanted to answer the question of how large of a sample would we have to have in order to be able to use a normal model, then you can take 10 divided by p, and that will give you the smallest sample size that would guarantee 3 standard deviations unobstructed with at least 10 successes and 10 failures. So do 10 divided by p or 10 divided by q, and then take whichever one is the smallest. Or whichever one is the smallest. So the smallest sample size that we could have would have had to have been 62.5 in order for us to use a normal model. Number 18. Smoking. Public health statistics for 2009 indicate that 20.6% of American adults smoke cigarettes. Using the empirical rule, describe a sampling distribution model for proportion of smokers that are randomly selected out of a group of 50 adults. Do you think the appropriate conditions are necessary for our analysis are met? So one, we want to make sure that they are randomly selected in order for us to use a sampling distribution model. That's to make sure that it's actually a representative sample. If it's not randomly selected, then we could over or underrepresent certain populations. So for instance, if we only asked a group of 50 adults that were showing up at a family reunion, it might be that if you have smokers in the family, that there's more likely to be other smokers in the family, perhaps, or maybe less likely, I don't know. But if there's any association at all, that would not be a representative sample, because some family reunions might have a lot of people that smoke and some might have nobody that smokes, just depending on culture and family stuff. I don't know. So we need to make sure that it's randomly selected so that we know that it's going to be independent and representative. So they told us that it was randomly selected, so we're good to go. 10% condition. So because we're sampling without replacement, meaning if we sample somebody, if we ask them if they smoke, we're not going to put them back in the pool and then select them again and ask them if they smoke again. So we are technically sampling without replacement, just like with a deck of cards, and so the probabilities are going to change. But once we've selected 10 people who smoke, there's 10 less smokers that are out there, so it's less likely that we'd find another one that would smoke. The probabilities technically have changed. So this can be overridden, the assumption of independence, as with the 10% condition, as long as we're sampling less than 10% of the population. Now 50 adults is certainly less than 10% of all American adults. So we are sampling less than 10%, so we can override it. The probabilities would change, but they're going to change so small that it wouldn't actually matter. It wouldn't change our conclusions. Good way of saying it. Success failure condition. So on this one, we need to make sure that we're expecting at least 10 successes and 10 failures to guarantee that we're not cutting off our normal model by a hard left bound of 0 or a hard right bound of n. So we're expecting on this one 10.3 people to smoke out of a sample of 50, which is more than 10, so we're guaranteed 3 standard deviations unobstructed, so we're good to go. Use the empirical rule. So this is the empirical rule. 68% of all samples we would expect to be within 1 standard deviation. 95% of samples we would expect to be within 2 standard deviations. 99.7% of all samples we would expect to be within 3 standard deviations. So you'll have to fill in the mean and the standard deviation using what we've learned today, but that's essentially what I want to see if they want you to describe it using the empirical rule. Number 11, coin tosses. In a large class of introductory statistics students, the professor has each person toss a coin 16 times and calculate the proportion of his or her tosses that were heads. Well, it sounds like fun. We could do that. The students then report the results, but the professor plots a histogram of the several proportions. So eventually it'll end up looking like this if we do enough of our simulation here. So what shape would you expect it to be? Well, as we increase our sample size, eventually everything turns into binomial or a normal model. So it would be unimodal and symmetric. Where do you expect the histogram to be centered? Well, 50% of 16 would be at 8, so we would expect on average 8 heads and 8 tails, but not every one of them is going to be 8. There's going to be variation in that. There were 7, 6, 8, 10, 11, 9. Those were all very common, it seems, in that case. So explain why the binomial model should be used instead of the normal model. Well, we're only expecting 8 successes, which is not going, and 8 failures, by the way, which is not going to guarantee us at least 3 standard deviations. So technically, we should not use a normal model. Instead, we have to default to the histogram, which would be our binomial. So should we be concerned that 10% condition when flipping a coin? Well, 10% conditions when sampling without replacement, but when we flip a coin, it's going to be independent. No matter how many times you flip the coin or not. You can flip a coin a million times, but you never really run out of possible coin flips, and so it's always going to be independent. Anyway, we're not sampling out the replacement, so each trial is independent. We're good to go. We don't have to worry about bias or anything like that coming in and messing up our random sample. So it'll be representative is what I'm trying to say. Should we be concerned with random sampling? No, it's kind of the same issue. It would be a representative sample. You can't really have any bias when you're flipping a coin, anything like that. So we're good to go. So our success failure condition uses 10 as a conservative estimate for the minimum number of successes. And that was because we had 9 times q, and the largest q would be 1, and so it could potentially be 9. But if our q is 50%, then half of 9 would actually be 4.5. So technically, we would only have to have 4.5 expected successes. And if we look here, that kind of makes sense because there's no way that 3 standard deviations is not going to be obstructed on this one. So we use 10 as a conservative estimate, like a worst case scenario. You have to have at least 10 successes and 10 failures, and that rule works every time. But if you wanted to, and don't do it on the AP test, just stick with 10. But it actually goes further. We can actually, we can show, depending on what our value for P is, our probability of success and failure, that we don't actually have to have 10 successes and 10 failures. But again, I'm showing you this just because you can see it here and you're like, wait, there wasn't 10, there was only 8. But clearly, we are not getting cut off within 3 standard deviations. So is it worth remembering? No, not really. Just use 10 for the AP test and forget I ever said anything. But if you want to know all the intricate details of stats, I'm your man. Not really. I mean, I'll try. I'll share all the cool stuff that I've discovered. Alright, so that's it. If you guys have any questions, please let me know. Tomorrow's assignment should be very similar to this one. I'll make sure definitely that the video is shorter as well. So I'll see you guys tomorrow, or whenever all the ice melts and stuff like that. But I'll see you guys around.